Between episodes 1 and 2 of Error Code, the Hackasat 3 finals were held. If you want to know more about the background and history behind the Hackasat program, I suggest you listen to episode 1 first, if you haven't already. Basically, there are 8 teams in the finals that compete over a 24-hour period in a capture-the-flag competition to gain control of a simulated satellite, scoring a number of points along the way. So what were some of the challenges in the Hackasat 3 finals? The winning teams were required to write up their solutions, and these are available on the Hackasat website itself. Basically, though, the challenges they encountered this year include basic antenna and maneuverability of the satellite, which is what they call SLA settings. There are then various challenges, including some using encryption, and toward the end, it appeared that all the satellites were starting to fail. But then, that was kind of expected, since in the final round, the teams were expected to fire malicious payloads at each other. So who won? For Hackasat 3, we have Poland Can Into Space in first place with a $50,000 prize. We have Space Bits Are Us from the United States with a $30,000 prize. And Solar Wine from Belgium, France, and Switzerland with a $20,000 prize. The team that won, Poland Can Into Space, is no stranger. In fact, they've placed within the top 3 in the first, second, and now third Hackasat competitions. And Solar Wine, they're also a repeat winner as well. But Space Bits Are Us, they gained their first time on the leaderboard this year. What's interesting is that the Hackasat 3 final was designed to preview the type of play we can come to expect in next year's Hackasat 4, the first in-orbit capture-the-flag sandbox. The physical satellite, Moonlighter as it's called, will launch with one of the International Space Station resupply missions in the summer of 2023. And this will be the basis for Hackasat 4 at DEF CON 31. This is the story of the digital twin built to simulate Hackasat 4 for Hackasat 3. And what happens next when the competition ends? How does this Hackasat mission continue? I'm Robert Famosi, and this is Error Code.
Yeah, so my background is more traditionally in aerospace background, a bachelor's and master's in aerospace engineering.
This is Logan Finch. He's the Hackasat technical lead, working with a company called Cromulus, a research and engineering simulation and training company.
Before I worked at Cromulus, I'm doing more cybersecurity work. Originally, I worked at another big defense contractor building real space systems. In college, I learned all the space math, as we like to joke and call it. So all the orbits, pointing of spacecraft, all the generic kind of space mission systems engineering. So like how those big systems come together from a low level to be put together. So that's what I did when I worked in industry on space systems. And then I was able to leverage that knowledge that I'd kind of built up over time to, having seen what some of these real systems look like that are fielded and, actually active, bring that to Hackasat and use that to help design these Hackasat specific simulated space systems in a way that looks realistic.
Like any elite capture-the-flag competition at DEF CON, Hackasat should simulate some of the real-life challenges and obstacles. In this case, Moonlighter, the name of the Hackasat 3 final, should ideally simulate what a hacker on Earth would have to overcome to first contact with and then manipulate a satellite in orbit.
Just building all these simulated systems, I mean, like we said, there's a lot of complicated moving parts, right? And fitting them all together and getting this whole thing to run in a closed loop fashion and have the performance where it looks realistic enough. It's a unique problem.
And so what you'll see in Moonlighter is you'll see the bit for bit copy of some of the things that not all of them or maybe parts of them, but some of them that are going to be available to the teams to use to compete with on orbit, right? So that's kind of never been done before.
This is Frank Pound. He's a technical advisor with the United States Space Force team that is hosting Hackasat.
And there's a lot of really novel, interesting spin-offs that are going to come out of Moonlighter and come out of Hackasat next year, but we have to sort of wait until that we unveil all that next year for what exactly that's going to be.
Moonlighter is both the name of the Hackasat 3 final competition and also the satellite that's going to be launched next year.
So it's like sort of a bitwise identical copy of what you would deploy to the FPGAs and to the small embedded systems.
FPGA, that's Field Programmable Gate Array. It's an integrated circuit that is designed to be configured by a customer or designer after manufacture.
And now, with what Logan's team has built with this, true to life simulation, try to simulate the reality of space. And, I think it's worth talking about that a little bit. The software, the flight software, is the real flight software that's in simulation.
One of the big things that we're developing for Hackasat, from a technology standpoint, is what we're calling digital twins.
Digital twins is an industry term, and it basically means that you create a bit-by-bit copy of a hardware physical system for the purposes of software testing. It's used in the manufacture of computer chips because it's expensive to take rare earth materials and to try them out on a chip just to find out that it didn't really work. So you use a digital twin of the chip and you plug that into whatever you're doing, and you can tweak and optimize the design before you commit to actual silicon. Pretty brilliant. So how is a digital twin different from a simulation? A digital twin is actually a virtual environment. And so the difference between a digital twin and a simulation is largely a matter of scale. While a simulation typically models one particular process, a digital twin can run any number of useful simulations in order to study multiple processes.
It kind of exists, in various forms. It's not exactly a new idea, but what we're doing is, starting from scratch, trying to build a digital twin system that is, representative, but also flexible in so much as that we can build in these interesting problems.
And all these problems would be simulations within the digital twin environment. We can have any number, which is what you want in a competitive capture the flag situation.
We are running a piece of software that's open source by NASA that we then customize on top of that's real spacecraft flight software that's running on real satellites in space right now. We take that and we build new applications on top of that that are specific to the challenges that we're running, somewhat intentionally. We don't necessarily want to, be taking real software that's in space right now and finding, that's not necessarily what we're doing with Hackasat.
So the software is generic in the sense that Hackasat is not interested in teaching people to cripple real satellites in use today, but models some of the possibilities of what might happen if they don't follow good information security best practices.
What we really want to do is drive industry and other parties to the space industry to look at their systems, look at what they're building, look at what they're designing, and build it with cybersecurity in mind.
So let's drill down on the simulation that Logan's team is building for this year's Hackasat 3 final. Previously, Hackasats 1 and 2 had hardware components in their final events. The idea was that real hardware is real interesting in terms of real challenges. But that won't scale, at least in terms of simulating what Moonlighter will be like in the next year when it's up in space.
Build representative issues into these systems without necessarily poking and making, giving some company or some manufacturer or some software a black eye and say, look, you have this exact problem. No, that's not really what we want to show. We just want to show that, look, if you don't design with good security practices, these are the types of things that can happen.
So with a typical digital twin, say the chip example we discussed a moment ago, that's one hardware system to model in a virtual space. And that's a challenge. But with Hackasat, it's not just the satellite with all of its software that has to be modeled. It's also the environment of space itself, the physics, as well as all the ground communications and all of that.
The ground up, we have a physics simulation. So that actually simulates the spacecraft in space, all the orbits around the Earth, the ground station having the ability to reach out and talk to it. So we do all those things that happen in real spacecrafts. You can't always talk to a spacecraft because it has to be over an antenna that you control, or stuff like that. So we're doing that, and then we also have all those like software elements. And because we can, build these things up from the ground up, we can build representative issues into these systems without necessarily poking and making, giving some company or some manufacturer or some like software a black eye and say, look, you have this exact problem. No, that's not really what we want to show. We just want to show that, look, if you don't design with good security practices, these are the types of things that can happen.
Logan's in a good position to know. Prior to working on the Hackaset project, he built these software systems for real customers.
So I've worked primarily on the ground software side of things, so building the software that controls, real spacecraft from the ground. So that's kind of where my mindset came from when building these systems. I got kind of an opportunity early in the pandemic to work from home and do some really, really cool work. And I took that opportunity because it had a lot of very interesting, both the context of building a competition from scratch, also space cybersecurity. I fully understand, having come from building these real systems, that it's a very, very important thing for both companies and the US government to be involved in.
Okay, so the ground station is going to have a network topography similar to any organization. It's going to have Linux or Windows operating system with various programs, some of which are proprietary. Yeah, this starts to sound like a familiar hacking landscape.
The ground station is just usually normal kind of server infrastructure running, normal software. Granted, lots of stuff is, being custom built by some of the companies that are fielding these systems. But at the end of the day, it's has all the same type of security issues that any sort of company that's running a internet facing piece of software has to deal with, and that'll be good enough. A lot of that's been worked on for a long time, but at the same time, that still doesn't solve all the problems of you're still pulling in data like weather and data from NORAD and stuff like that into the system that is from the internet or from other sources. So you still have to build these systems from the ground up with security in mind. And I think that that's just now taking off in industry, where it's really being pushed by both the government as a customer, if they're building a satellite, whether that be a weather satellite or other satellite, building these systems safely.
So with hacking, say a water treatment plant and an ICS capture the flag, you have servers on the ground that are available 24/7. With space systems, it's a little more complicated. Okay, it's a lot more complicated. So you actually have two systems to keep in mind. One is the satellite in space, but there's another piece you have to keep in mind, and that's the ground station. The ground station is just as important as the satellite itself. The ground station has to maintain contact with the satellite as it passes overhead, and in that short window has to upload and download whatever data that needs to be shared. And often you don't just have one ground station, you have a bunch, and they can provide nearly continuous contact with the satellite, although that rarely happens, nor is it absolutely necessary. So, in episode 1, we talked a lot about the satellite in orbit. Let's talk more about the ground station and its vulnerability.
You have the whole other side of things, the commercial side of space, and all these tiny little companies that are starting up, that are building, that have plans to build large small sat constellations, and they're facing these same problems, but with a fraction of the resources to build these systems in a safe way. So with Hackaset, we have a unique opportunity to really evangelize that how important it is to, from scratch, try and build these systems in a way that is sustainable, maintainable, and safe. Because as time goes on, all these systems are becoming more and more important to the global economy, to weather prediction, you name it. There's probably some part of it that's in space that has an important part of some global system, and as we become more and more dependent on them, the stakes get higher and higher on what a mistake could cost and result in.
The ground station software. I mean, there's all sorts of things going on in the ground station, the mission operations center for the satellite. So, and then you have the satellite itself that it needs to be maintained in orbit. And other parts of the satellite would be the specific mission parts of the satellite. So they have their own custom software that manages that. And you have the downlink and the communications software. So, and many times this is connected to the internet because they need to move that telemetry around to the different entities that are controlling different parts of the spacecraft. And so you have to be very careful to secure every bit of that line of communication. And then you have cross communication between these different components, and you want to read health and status. Like one group would want to see, what's the health and status of the satellite? So they need to pull data from this other group. So there's a lot of gateways involved in a lot of different areas where, adversaries or malfeasance could affect the mission. So the ground station, yes, is a core part of security. And if you don't have good ground station security, think of it this way. So there could be ground stations that control thousands of satellites. So if the ground station's compromised, then you have potentially thousands of satellites that are compromised.
So what happens when an inexpensive ground system gets hacked? At DEF CON 30, Leonard Walters presented what happened when he peeled back the reflective surface of one of Elon Musk's Starlink dishes. Starlink is a passive system in that it's designed for internet usage, not complicated payloads being uploaded to the satellite itself. But it serves to remind us that the ground systems themselves are vulnerable too.
Good morning, everyone. Thank you for being here. This talk is titled Glitched on Earth by Humans, a black box security evaluation of the SpaceX Starlink user terminal. A quick introduction on Starlink. I guess everyone knows this, but for every satellite internet system, you need a space segment and an Earth segment. In the space segment, we have satellites. These satellites can, in some cases, communicate with each other over laser links. And the idea is that you as a user buy a user terminal that sends your data up to the satellite relays it back down to Earth through a gateway. And in this way, you can access the internet. Now, for some reason, SpaceX wouldn't give me a satellite, which meant that I had to buy a user terminal and try to get in it that way. So we bought the user terminal, we put it up on the roof of a university building and connected it to the network. Everything was working well, but at that point we just had a second internet connection and there wasn't that much to do with it. So I started looking at what other people had done or what other people were working on at the time. So the top three, or the first three videos on the top were already out when I started working on the user terminal. So some people had bought the user terminal, tore it open to see what was on the inside. The video by the signal pad went in more depth about the RF side of things. And then when I started working, some other people were also working on it, like Colin O'Flynn did a teardown with a blowtorch, and he started poking at the board a bit more than the others. There's a nice blog post by Oleg on the Wi-Fi router that you get with the system. And then Dan Murray did a teardown of the Square user terminal and even made a 3D printed case for it. Now, one thing that was missing for me, at least in all of these videos and teardowns, was that I was mostly interested in the security of the system. And that's what this talk is about.
What Walters revealed over the next hour is that it's possible to push a voltage fault injection attack on a Starlink user terminal. To do this, he created a tool using low-cost, off-the-shelf parts. And with that tool in place, he was able to obtain root access to the Starlink communication system through glitching. What's glitching? Glitching is when power, high-temperature sensors, or even clock signals are interrupted. This can cause the CPU and other processing components to simply skip instructions or interrupt an executing program in ways that allow an attacker to slip malicious instructions into those processing gaps. The mod that he created is comprised of a Raspberry Pi microcontroller, flash storage, electronic switches, and a voltage regulator. Once attached to the Starlink user terminal, he was able to launch fault injection attacks to temporarily short the system, which allowed him to bypass Starlink's security protections. Walters was then able to explore the Starlink network and its communication networks. I should note, however, that all of this was responsibly disclosed to SpaceX before the public exposure at DEF CON 30. So if you're going to create a HackSat competition, You actually need to model a ground system, which we said is similar to a network you're familiar with, but also model the satellite. And with that, you need to further model the satellite's environment. In fact, you need to have 3-axis control, and all this access has to be available for only short periods of time as satellites pass overhead. So here's where the modeling, the simulation, starts to get very, very complicated.
So it's a really interesting balancing act that I didn't necessarily realize coming into this, that you'd have to, work your way through when building these sort of systems.
So now that we have the environment, we need to create the scenarios themselves. So how did Logan and his team go about creating that?
I'm more familiar with building the low-level technical details of a large space, simulation, and all the lower level nitty-gritty to kind of build up something that looks like a system. Because that's basically what we're doing, right? We're taking from scratch, building a simulation of a full space mission from the ground up. So we have a satellite ground station, a ground system, other pieces of software that would usually live in those sorts of systems, and then we have a simulated communications link with different levels of realism there, depending on what we're trying to do for a given year, a given set of challenges.
So we talked about the elite hacker teams having to understand orbital systems. So too did Logan have to reorient his way of thinking. He's used to thinking about how satellites will function in space. With Hackasat, he needed to know how a satellite might not function in space.
Usually on that side, we try and emulate the actual flight processors to make it look as realistic as possible and make it actually look like a real processor running real software in space as much as possible. And then we try and link all that together with physics and other interesting elements to make to bring realism, all the while trying to make sure that we think about this from a cybersecurity standpoint, which involves building in vulnerabilities and making interesting cybersecurity challenges just to raise awareness around this whole topic.
Given all that, the resulting dashboard for Hackasat 3 is a bit intimidating. With all the streaming real-time telemetry data and the visualization of where the satellite is currently orbiting the Earth, it can be hard to focus on the real problem, to stand back from all the gosh wow of it all. And it also raises a very real question about the end goal here. Certainly they didn't just build this for one capture-the-flag competition.
Building all these simulated systems, like we've said, there's a lot of complicated moving parts, right? And fitting them all together and getting this whole thing to run in a closed loop fashion and have the performance where it looks realistic enough. It's a unique problem, but it's also very useful because with one of these digital systems, it's if you break something or you crash something, even at the lowest level of what would be the hardware interface, I can just respin this thing up from the ground up and it's all good again. There's no risk to real hardware, to real things, right? Which means that you can really it's a real playground and test bed for developing cybersecurity capabilities, defenses, all that kind of stuff in a way that's safe and approachable to both these teams and anybody else who wants to do this sort of research.
So all this work that Logan and others are doing for Hackasat 3 is publicly available. It lives beyond the competition itself as a means to both train and to model different behavior of the thousands and thousands of devices in orbit today. But what happens to this effort once the competition is over? What happens to the digital twins?
We want to be able to, have a space system and use that high-level kind of hand-wavy representation of reality to showcase interesting problems.
One interesting problem occurred in November of 2021. The Russian government fired an anti-satellite rocket into orbit. And while they were targeting their own satellite for the demonstration, they made a complete mess of it. Here's ABC News.
This morning, outrage from U.S. officials after Russia carried out a missile test early Monday, firing an anti-satellite missile into space, obliterating one of its own satellites and creating a vast debris field that's now orbiting Earth.
The test has so far generated over 1,500 pieces of trackable orbital debris and hundreds of thousands of pieces of smaller orbital debris that now threaten the interests of all nations.
Some of that debris coming dangerously close to the International Space Station, which is currently carrying 4 U.S. astronauts.
We were recently informed of a satellite breakup and need to have you guys start reviewing the safe haven procedure.
The crew quickly putting on their spacesuits and taking shelter in one of 2 spacecrafts docked at the station, which can return them to Earth during an emergency. It wasn't just Americans taking cover. The ISS is currently home to 2 Russian cosmonauts. The crew sheltering for more than 2 hours until they were finally given the green light. Secretary of State Antony Blinken slamming the Russian missile test, calling it dangerous and irresponsible, and adding that the debris will remain a threat for decades. Just 1 week ago, the space station was forced to fire its thrusters to dodge debris from a similar anti-satellite missile test, which China carried out back in 2007. And officials also say the debris field from the Russian missile test could also endanger the Chinese space station, which is now home to 3 astronauts.
While deliberately crashing one satellite into another is a bit extreme, Hackasat has the ability to show the space industry today how a software vulnerability might result in a satellite losing its ability to remain in control.
One of the biggest value propositions of Hackasat, though, is that we can demonstrate these catastrophes in a sort of a safe detonation chamber without causing a massive cloud of space debris by demonstrating a software vulnerability that causes a satellite to collide with another one and create this debris field. With Hackasat, we can do that in our little detonation chamber safely here on Earth in simulation like Logan is describing, and show people, indeed, if this type of vulnerability exists and somebody figures out how to weaponize that vulnerability, this could be the end result. And people's eyes get really big and they go, oh, wow, so you can really do that. And we're like, yeah, you can really do that, right? So, and it sort of amplifies the need to be able to simulate these things at scale.
Part of the, the mission of Hackasat is to try and show the companies that are doing this that, they should adopt these kind of best practices going forward. So we try and take realism as a venue to build things that look real and address real issues like supply chain injection, just regular old software vulnerabilities, architectural vulnerabilities, all those kinds of things that exist in real things, but then, don't actually use those, but kind of build something from scratch that looks realistic.
So what they did this year at Hackasat 3 was to build out that real satellite as a digital twin, as a way to prepare the teams for next year.
In addition, these digital twins can be used for training and raising awareness. So we can build these systems because they're easy to replicate, easy to deploy. It's close to the point where, anybody who has an interest could take something like this and set it up and use it as a sandbox. On that topic, we published all of our software and, game setups for all the Hackasat events. They're available, for anybody to go download off our GitHub site for cromulence, and that's part of the way that we give back to this whole community is we provide all this interesting information for people to go look at if they have an interest and learn and start hopefully even inspiring some of the younger folks that are just getting into this industry to get interested and start building understanding of this so they come into industry. Oh, look, I've seen all this stuff. We really shouldn't do it that way. We should try and do this more securely, and that's a really big opportunity for both us, the company that Frank's doing, is pushing a lot of the same stuff, and just the government, Air Force, Space Force, and the AFRL to really push these sorts of things and raise awareness across the board.
And all this work can also go toward actively modeling next year's competition on a real satellite. I mean, the digital twin can give them a head start on what might work best for Hackasat 4.
Eventually, we're building up to next year where the game will be in space on a real satellite. So it's a unique opportunity to take that realism up to the real level, right? And actually showcase things that really can only happen in the real physical system. But also, we want to show what the stakes are of a real physical system. And that's what, having a real satellite in space allows you to do. It allows you to really drive the point home of what what can happen, but at the same time, build something that we can reset and get back to a known state to be able to run a CTF in space. So that's a whole other unique problem that we're working for next year. I think it's going to be a really interesting thing for everybody to watch and see what happens. And we're in the design process for all that kind of stuff, so we can't really discuss much more than what we have. But at the same time, I think it has the opportunity to really show off what can happen, right?
What's being built here is a new way of training people. So instead of focusing on a training environment where you have like this sort of PowerPoint driven classroom environment, you're now putting people in the driver's seat. You have the ability to do that. You're putting them into the operator seat on day one without any fear of getting hurt. If you imagine, back in the early days of aviation, when you got in the seat of the aircraft, it was sort of like, am I going to make it back or not? And if you weren't a good pilot, there's a good chance you would die. We fought through all that stuff, but now with spacecraft, with the simulation environment, I think the legacy simulation environments were this great big, server that was on a desk, and it had all of these, big components, and there was only one of them, and so. Yeah. It was just as fragile as the actual spacecraft, although you could, reboot it and restart it.
It's like the early days of computing, when people would queue up to run their stack of punch cards on the computer, and if the person ahead of them screwed up somehow, they would have to reboot the entire system before the next person in line could continue.
It's also very useful because with one of these digital systems, it's if you break something or you crash something, even at the lowest level of like what would be the hardware interface, I can just respin this thing up from the ground up and it's all good again. There's no risk to real hardware, to real things, right? Which means that you can really play. It's a real playground and test bed for developing cybersecurity capabilities, defenses, all that kind of stuff in a way that's safe and approachable to both these teams and anybody else who wants to do this sort of research, right?
But with what has been built for Hackasat, you've got virtual machines that are true to life simulations that you can scale in the cloud. So instead of one, you could create thousands of them, right? You can spin up a constellation of something to simulate like Starlink, or something to simulate another communication satellite constellation from another vendor, with a little bit of tailoring to make it look and feel like that. And then you've got the entire cadre of the new Space Force, who are going to be able to need to understand these things very quickly. So you could plop this into a classroom environment, get them training and understanding on day one, put them through some Kobayashi Maru simulations where there's no possible way for them to succeed, and teach them what failure looks like in the safety and comfort of a air-conditioned classroom with no fear of destroying a $1 billion satellite.
Okay, you knew we couldn't talk about space without dropping at least one random Star Trek reference, right?
On a lot of these legacy systems, that yes, they had some ability to test things on the ground and do that, but a lot of times it was like ground spares of like real components or other things that were a very limited resource that you had to be share between all the people who are needing it, or maybe one or two of them exists period. Because of that, you had to be very careful, right? And it made everybody very, very risk adverse, testing and trying, more risky things, which, a lot of the cybersecurity, tests that you may want to do or research you want to conduct, there's some level of inherent risk, and you don't want to break a piece of hardware or something that's unique that only 4 people know how to set up and fix, and those 4 people might not even be available, right? But with something that we're trying to build, is we want it to be all you need is a VM or a workstation with enough CPU and RAM, and you can spin this thing up and it'll self-configure and everything will just start up and it'll look real enough to do all these interesting things in a safe, easy, accessible way.
I just had this vision of one of my first computer science classes years and years ago. It was this legacy class, and they still used a mainframe, and you had to sign up for time to go run your programs on this mainframe. And if your college roommate signed up before you, or you didn't get in the right slot, then you had to go in at like 8 o'clock at night, and you're like, I don't want to go in that late. So it's kind of like with these simulators that they had in the legacy space community. They were kind of like these old mainframes that you signed up for to run your program on. You had to wait in line to use them, and you had to be very careful, and you had to make sure the right experts were around to manipulate some component that was like one of a kind. So I had just had this vision in my head when he was talking. I'm like, oh my God, that's how it used to be. And we're Logan and his team are sort of changing all that, so it's just way more efficient, way more useful, and there's a ton more value in what's going to be available.
T-minus 6, 5, 4, 3, 2, 1.
Space Force is going to be building a satellite. It's called Moonlighter.
Moonlighter is going to be the first hacking sandbox in space.
It's going to be a 3U spacecraft. It's going to be put in orbit sometime early spring next year, maybe summer, and it's going to be a key part of the competition. And we're sort of treating Hackasat 3 as like the training ground to introduce people to how to time the orbits of the spacecraft to perform their cybersecurity skills. As they make mistakes this year, I think we're going to learn things, and they're going to learn things too. That's going to really set us up for success with the real spacecraft on orbit next year.
I don't know about you, but I'm pretty stoked to be able to see hackers influencing an actual satellite in orbit around the Earth. This is going to be really cool. I'd like to thank Logan Finch and Frank Pound for talking about their experience with Hackasat 3 this year. Hey, so I'm just getting started with Aerocode, and I have some really cool stories ahead within the IoT and embedded security space. Stories with Joe Grand and others coming up in the next few weeks. DM me at Robert Vamosi on Twitter with your feedback. I'd really like to hear from you. And if you like the show already, then I hope you'll subscribe wherever you get your podcasts. Aerocode is written and produced by me, Robert Vamosi.